My talk today is going to be like a little overview of newish C++ 23 features. But instead of giving this, well, overview over a grab bag of different features, I wanted to structure this a little bit different and go over a very typical thing we do a lot of the time, that is defining a class, defining a data structure, defining something in code, and then I will go over some new C++ features that will help us doing so. Now, when I wrote the abstract, I wanted to look at the new C++ 23 features, and when I wrote the talk then, I found out that there are not that many relevant 23 features. So this is going to be like C++ 22, C++ 26-ish. Okay, some preliminaries. All the code samples, and there will be quite a lot of code samples, did compile with some compiler at some point. I put the gob-build links on each one of those samples. Everything is using namespace did for brevity. And all the code samples use UTF-8 encoding. Although, of course, on the slides you can't tell. But this is now an officially supported file encoding. And this is obviously the best C++ 23 feature right out of the gate. So before we begin, what actually is a class? What are we talking about today? So typically we might say, well, a class is a unit of data and code. But that's, well, it sounds very simple, doesn't it? So I went back a bit, and I wanted to find out what the inventor of the first object-oriented programming language of Smalltalk had to say. And there's a great paper, The Early History of Smalltalk. And he says that instead of dividing computer stuff into things, each less strong than the whole, like data structures, procedures, and functions, each Smalltalk object is a recursion of the entire possibilities of a computer. Well, that's a better definition, isn't it? Still just means it's data and code, essentially. But the recursion of the entire possibilities of the computer, it sounds like the possibilities we have when we program, right? A bit further in the same paper was a different quote. It doesn't have anything to do with my talk, but I still want to share this today. This is something to take home today or to take later to the bar. Because he was developing Smalltalk in the 60s, and he said he was thinking a lot about the potential to amplify human reach and bring new ways of thinking to a faltering civilization that desperately needed it. So this is something to discuss later at the bar, if that's what we're doing. Is that what we're doing day by day in our work? Because that was his goal. That's a pretty good goal, I think. So now back to the subject at hand and simple C++. So a class is a unit of data and code. In C++, that means it has constructors, destructors, base classes, access control, member functions, template arguments. So these are all syntax. But a class should have some meaning. That's typically what we start with, right? That's also what was such a good idea about Smalltalk, to give things a representation, things that have actual meaning in the real world. So when we develop a data type, this could be a simple value, it could be a container, it could be that we want to write a resource wrapper, or something that is maybe a global singleton, and we want to guarantee that it's always a singleton. And based on these semantics, we can deduce what lifecycle this thing should have. And what lifecycle an object has in C++ means what constructors do we have to implement? Do we have to implement a destructor, etc.? So this is how we give shape to the lifecycle of an object. And now when I say, what constructors to implement, and which ones, and do we have to implement a destructor, you are probably already thinking about that image. So this is the image from a talk by Howard Hinnant in 2014, where he explained when move semantic was still a new thing, what happens if the user declares a constructor, and which constructors will then be implicitly defaulted or deleted or not declared, etc. So that's perfectly fine. That's perfectly true, of course. But that gives, I would say, an overcomplicated view of the entire situation. That's not what I typically look at when I define data types, because there are actually relatively few cases that happen very often. In these cases, we can think in. And we have to, know how to implement those semantics. So the first one I mentioned were simple value types, right? Simple value types, the hand-waving definition is, well, that's anything that should just behave like an integer. Now, there is a better definition. There are very formal definitions. This all goes back to Alexander Stepanov's paper, Fundamentals of Generic Programming, where he developed this idea that there should be concepts and types should fulfill those concepts, and then we talk about the operations we can do on those types. And there were a lot of talks about value types in recent years, for example, by Victor here. Regular Revisited was one of those talks that summarize how we think about value types and why they're important. So I don't have to repeat that here. In summary, simple value types should be default constructible, they should be copyable, movable, assignable, and comparable. And that means we call these types regular types. All built-in types, integer for example, are regular types, and SDL types are typically, I hope always, regular types. Well, containers are. String and vector, for example, are regular types, of course. And the C++ guidelines tell us to make concrete types, here that means things that represent actual concrete things, to make them regular because regular types are easier to understand and reason about than types that are not regular. So we want to make our own value types regular as well for reasons of simplicity and consistency. Now, what do we have to do in C++? Well, we have a simple value type, like this, contact. What do we have to do to make this regular, or at first semi-regular? As long as it doesn't have a comparison, it is not regular, it's only semi-regular. What do we have to do? The answer is nothing. So here this type only contains SDL type, strings and vector of strings, and variants and optionals, and this type is by default already a regular type. The compiler will generate a default constructor for us, move construction, move assignment, copy construction, etc. So the rule of zero, I might have to put the URLs on those slides. The rule of zero is documented on CPP reference, for example, means that for simple value types that consist of types that are in themselves regular or semi-regular, we don't have to implement any special member function. This thing will be regular by default. Now that is great. And that, like I said, that definition is recursive. So if we have another type address that is also a regular type or semi-regular here, then we can make that a member of contact as well. And we will still have a semi-regular type. Great. Everything is fine by default. Now there's another case where we maybe want to write our own container. That container will probably have to manage its own memory. When we have to manage our own memory, we might have to write our own destructor. When we manage memory and we want to have a copy operation, then that copy operation must make sure that the new copy allocates memory and copies the data over, etc. So we need to implement the copy operator by hand. And when we manage our own memory and want to have a movable type, we might need to implement the move ourselves to take away the storage from the R value and move it into ourselves. So it turns out that very often, this is the rule of 5 or 6, once you start implementing one of those constructors, you actually have to implement all of them correctly. So if you only implement the copy construction, then the move will be disabled, etc. So there's a very good blog post by Jonathan Mueller, also known as Funetan, about special member functions here. Now the result, and that's important, is if we declare all of them and we implement them all correctly, then this container will also be a semi-regular type and behave like a value type. And that's what we wanted. So the third case, where resource wrappers, these are little objects we write that hold a file, a database connection, etc. These things are almost always move-only types. We don't want to copy the database connection. There's only one of them. So we don't want this object to be copyable, but moving is perfectly fine because we can just hand over ownership of the database or of the file. So that's a very simple implementation here. We have a little wrapper that wraps our good old std file pointer. There we go. The std file pointer might be null, then we don't have an open file. We have a constructor that opens the file, of course. We have to implement the destructor that does the file close. And now we would get a defaulted copy constructor or copy assignment that would be wrong. So we don't want that. So we implement our own move construction. And then we also have to implement our own move assignment to get the correct semantics. And now we have a movable file type, and that can't leak that std file pointer. And what I like to do is I like to extract something here. What we have in our code base that used to be pretty common, for example, Boost had a non-copyable type that didn't know about move semantics, so that was 10 years ago. I like to write my own little non-copyable type that does nothing more but default the move construction and move assignment operations. So by consequence, this type is not copyable, and then I like to write this in this somewhat declarative style, that I have a new type file, and that file should not be copyable. And then I implement the necessary operations, but if I do this wrong and I generate a copy by accident, I will get a compiler error because non-copyable is not copyable. And here we get the first new C++ 23 feature in relation to move-only types, and that's move-only function. So move-only function is itself a move-only type. And that those two are very handy together, because you might have had the situation that you had a file or your database wrapper, whatever, and that was a move-only type, and you wanted to move that into a function object. So like here, I want to move that file into the lambda capture, and now I have that lambda that owns that file, but now for some reason, I have to make this into a polymorphic std function object. And now this would not compile because std function was a copyable function. So it would require the lambda to be copyable, the lambda would require its capture to be copyable, and it wasn't copyable. So now we have move-only function, and this will work. And it turns out, at least in our code base, that a surprising amount of functions can be move-only functions, where you maybe want to define some callback to, let's say, a button or so. And it's just a function object that you move in, and then the button holds its callback. And there's no need to actually copy it anywhere. So these two are very handy together. And then the last one is this here. Global singletons, could be anything. Mutexes, for example, by themselves are of course not copyable or movable. Could be any other global singleton you want. Some RAI wrappers that are just objects that exist on the stack to clean up something. They are often non-movable and non-copyable. All objects that need to have pointer identity probably don't want to be movable or copyable. And here we do the same. We can declare a little non-movable type that deletes copy assignment and copy construction derived from that, for example, and thus declare an object to be non-movable. Okay, so that was a simple revisit of the familiar lifecycle rules that we have. So simple value types we can declare with the rule of 0. For more complex value types, if we want them to be regular, we have to follow the rule of 5 or 6, depending on if we count the default constructor. And the result should be at least semi-regular value types. And then we have non-copyable resource wrappers and non-movable singleton objects. Now, while we're at this subject, one warning. We cannot actually check using concepts or static asserts if types are actually really moved. So std semi-regular, the concept says a type is semi-regular if it is movable. But C++ is super backwards compatible. When move was invented, I think we practically decided that any object that just has a copy construction is also movable. The move just falls back to the copy operation. So here, this perfectly holds. It's semi-regular, but since we've implemented the copy construction, no actual move will take place. We will copy. So that's a bit unfortunate. And I've hidden another C++ 23 feature there, std println, which is using the same formatting API as did format, but makes the hello world example much, much easier. Okay, so yes, this object will always be copied and not moved. So I will talk a little bit more about regular types. Then I will talk a bit more about compile time evaluation and what we can do in C++23 at compile time, how compile time allocations work, how we can make types formattable, and then in the end, why we have explicit object arguments, or deducing this, as it's also called. So our value types at this point, following rule of 0, they were just semi-regular. They didn't have a comparison operation yet. How do we make them regular? Well, that is super easy as well. We just default the spaceship operation. So this will, by default, do the right thing. In this case, it will do a member-wise comparison of those members as long as those are all comparable, of course. Who here, by the way, little question, who here is using C++23 in production already, maybe? C++20. Okay, that's quite a lot. It's much more than in the meeting C++ survey that Jens posted, I think, somewhere. Sometimes we do have to implement those comparison operations ourselves, unfortunately. And defining equality can be surprisingly difficult. So if you read this paper by Alexander Stepanov, then he says, well, value types can actually contain references or pointers or handles, maybe just for efficiency reasons. Maybe you have a value type that contains data from a file. You don't want to read in the file. It's perfectly fine to hold the file. But if you compare that type to another type, object of the same type, then you actually have to compare the file contents if you want to have a value type. It shouldn't compare the file reference. So far, implementing equality can be difficult, but it's of course always a valid choice to say, well, as long as I don't need it, and I'm not sure about the semantics this comparison should have, maybe I shouldn't implement it in the first place, right? Otherwise, you're going to implement the wrong thing anyway. So you can defer this decision if you need to. But sometimes you need to. So here I have a little complicated type. It's a toy example, so I didn't want to think too hard about what this could mean. So let's say we have a type T that has a little bit of data, just an integer, and it also has a unique pointer to some sibling. This is going to be some data structure. But now this is meant to compare as a value type, so I want to make a deep comparison. And well, I'm not thinking too hard about this, so I kind of hand-wavingly implement my comparison operation. I'll just say, well, usually I want to compare them by data, but if left-hand side and right-hand side both have a sibling, then, well, compare those by value and be done with it. So I don't want to show this too long, because that's wrong. And that was just an example I had to come up with to say, well, you can implement equality wrong if you're not careful. So this example here has an inconsistent equality operation. It's not a valid total ordering. So when I think about implementing equality for value types, I think about partitioning the universe of all possible values that a type can have. And every comparison I make has to make like a clean partitioning of all possible values into, well, two groups. So here what we could say, for example, is, well, if we want to look at those types, well, first maybe we should partition them into all of those that have a sibling and all of those that don't have a sibling. And then I can go down the list of members I have and then compare the first group further recursively by the value of their sibling and those by the integer data. And then I still haven't compared the first ones completely, so these are even more partitioned. So then I can go down this partitioning and make sure that somewhat all of my values are on a unique point in the spectrum down here. So I know I have gotten this wrong in the past once. Who knows who he has implemented equality wrong? At least once in his life. Yeah, thanks. I'm pretty sure there was some example like that where I didn't think too long about this. Some example like this toy example. So this is how comparison would look. It's a bit repetitive at the moment, I find, but that's the way it currently is in the standard. So we first compare by having a sibling. Here I'm doing this shorthand conversion to bool. And then I'm in a state where I know both of my left hand and my right hand side have the same property. And then if both of them have like this pointer, then I compare recursively by the pointer value. And then I'm done and just compare by the integer. Okay, defining equality, not as simple as I had wished in the past sometimes. So back to the value type. What other property do we have by default? Who has an idea? What other property does that thing have?
Assigning to itself works?
Does the default assigning or move? Well, assigning, the self-assignment, I hope the compiler does the right thing by default. I do hope so. I think if it well, I didn't check the implementation, but it should. No, I mean this is by default Constexpr constructible. I didn't have to do a thing. And Constexpr is super powerful. So of course it's constructible. It's assignable at compile time. It's even comparable at compile time, and I didn't even declare this Constexpr. And then in C++23, of course, we have a whole new range of algorithms, for example, that are now also compile time. So fault left, for example, I think is an entirely new algorithm in C++23. So we can do a whole lot more compile time calculations. And Constexpr has always one cool feature. You see here, this optional, this isn't initialized. So who knows what happens if I do this at compile time? You get a compile error, and you get a super nice compile error because it tells you exactly what you did wrong. And you would wish you had this at runtime instead of a crash, right? It just tells you, oh no, you forgot to initialize that thing. So that's pretty nice. So Constexpr, always the same since C++20. We should make everything Constexpr as a habit as much as we can, including functions we define. If it is just possible, then it doesn't cost us anything. But your future self might need it and will thank you. And as we've just seen, compile time evaluation means no undefined behavior, no lifetime issues, of course, no static initialization order problems, etc. We don't only have Constexpr though. We also have constinit, and of course, the good old const. So what exactly is the difference between those two? So good old const declares a global variable. Here I'm only talking about variables of, I think the technical term is static. God, what was it? It's going to come on that slide. Static lifetime, static initialization. Duration, storage duration, static storage duration. So global variables, essentially. Const, of course, means the variable is immutable. The compiler might be able to calculate its value at compile time if initialization is simple enough, but it's not required to, and it might not work. You can run an entire constructor. You can do std_printf, of course. Constinit means it is not const, but it is guaranteed to be initialized at compile time. Very good, because that means you don't have that static initialization order fiasco problem. Okay, so constinit means it's guaranteed initialized at compile time, doesn't mean it's const. So of course we can have constinit const. Constinit const means that we have a variable that is immutable and initialized at compile time, but that's not the same as Constexpr, because Constexpr also means that this this variable, has to have a Constexpr destructor. So you can have a constinit const variable is immutable. It does have a Constexpr constructor, but its destructor can still do std_printf. And the Constexpr destructor cannot do std_printf because that's not, or std_printline now. That's not Constexpr. Okay, so this holds for variables with static storage duration. And now, of course, well, if you followed along, you see these were a lot of C++20 features. So I was under pressure to show you some more new C++ features. And here was a cool one. Now you do all this compile time evaluation, you need compile time asserts, of course, static asserts. And so far, static asserts can either show, a literal message, or you can omit the message and then he will just prints out static assertion failed. Well, we don't learn anything about T or T2, and that's a bit unfortunate. And sometimes you can build your own little contraptions so you get more information about the compile time types in the template initialization information, but that's not so cool. Instead, in C++26, static assert can have error messages that are computed by Constexpr functions. So this is meant to be used with std format, but std format is not Constexpr yet. So I've built my own little poor man's std format here that just concatenates the input strings, and then this is, well, kind of a very simple std format formatter, right? And indeed, that works and gives a helpful error message that my two arguments here are indeed not the same. And the requirements here on the right-hand side are very simple. You don't have to compute a string, actually. You have to compute some type that has a size member and that has a data member that is convertible to const card pointer. And then that's C++26, you get nicer static assert error messages. Now, following in new Constexpr features, unique pointer can now be used in Constexpr expressions. And it couldn't before. So what do we do with that? Because now that's unique pointer, okay. This, of course, doesn't work. It will give us a compiler message as before, where we still have the UB checker in Constexpr expressions. So it will know that this is a null pointer and tell us at compile time. Nice. But how do we use that? Of course, that's not going to work. That's also given us a compiler error. It's going to say that the T constructor is not a constant expression anymore. And why is that? Well, we are making an allocation, and that allocation now, well, it would have to exist for the lifetime of our program, right? Because we just generate a global T object. So that's not going to work. So how do compile time allocations work? Because they do work, otherwise we wouldn't have Constexpr vector and Constexpr string. And the rule is very simple. You can make allocations using operator new and operator delete and T allocations in compile time expressions, compile time evaluated expressions, as long as those allocations do not survive the compile time evaluation context. That means once you've calculated your compile time variable, everything has to be deallocated again. That means these allocations are transient and not persistent, as I think the standard calls it. So this doesn't work. This would work, right? I'm constructing and destructing my T down here. It's not terribly useful. It might be more useful when I do something like that, right? We can declare more functions Constexpr because these Constexpr functions might internally do something with unique pointers, like they did with vectors and strings, and hopefully soon more data structures like maps, etc. And they can still be declared Constexpr as long as all the allocations are deallocated once we're done with the compile time evaluation. And what does this mean? Well, this means that together with the compile time UB checker, you can actually, so if you need to do manual memory allocations somewhere, and I hope you have a very good reason for that, then by declaring that code Constexpr and trying to evaluate it at compile time, you could get a compile time checker if your logic is correct. So if your logic is incorrect and you would leak allocations, the compiler would be able to tell you. And that's pretty cool, right? So years ago, there was a talk at CPPCon about people who did the same for UB. They implemented a kernel for something, and they declared everything Constexpr and evaluated their kernel at compile time. They wanted to run it at runtime, of course, but they tried to evaluate it at compile time to make sure it didn't have UB. And that's a pretty cool feature of Constexpr. Okay, so now we have a regular value type, we get default comparison, so it's actually regular, it is compile time evaluatable. What else do we want? Well, it would be nice if we could just print that thing. If that would work with our new std println and std format API, right? So there's also a new concept that's also new in C++23, formattable, and we want that to be true. Now, what do we have to do to make that true? We have to specialize std formatter. So std formatter is the customization point for std format, and std formatter has two functions that we need to implement. The first function is the parse function, that is Constexpr. It is Constexpr because the main feature of std format is that it does compile time checking of your format string. So that's what we have to or can implement for our own type here. Now at first, let's say we don't do anything here. So the parse function gets a parse context, and the parse context gets the range of the format specifiers for your type. So we can parse them. Now let's say we don't have any format specifiers, so we don't do anything for now. And the format function is not Constexpr, of course, gets your type, a context here, and a format context. Format context contains, for example, the locale, and what interests us most here is the out function, that is the output iterator, of course. And into that output iterator, we can now write our type. And here I'm using std format2, using a format string again that just prints, well, parts of my data out to that output iterator. So that's like the simplest thing you could do. But you can implement this parse thing. Parse, like I said, gets the parse context. The parse context gets an iterator to the beginning of the format specifier. Now let's say I want to implement a very simple format specifier, which is format specifier P. That means be more private and don't print my H into every format string. And you can also look at the standard library implementations. It is often really as simple as going over that range, checking. Now I might have to do an end check before that. But checking if the format specifier is P, and then I store my state, and then in the end, you should check that you have fully consumed the input range of format specifiers. And if you haven't, then you can throw and should throw an exception. So that's relatively straightforward, I think, once you figured it out in the documentation. And then in the format function, we can do two different things. So one option would be that depending on the be private member, I use std format2 again with different format strings, with a very short format string, and here I have the full format string. The advantage here is that std format gets a literal format string, so we will get compile time errors if we have made any mistake here in the format specifier, right? That's the value of std format. It will check this at compile time. That's maybe a bit annoying when you have different types of format. So in C++26, we can do something that will only get us runtime errors, but it's a bit more convenient. So we can build a format string at runtime, here using a simple std string. And then there's a new type, std runtime format, that will not get us compile time errors, of course, but it's a bit more convenient to use. Okay. So there's a bit of CPP reference here. There are, in C++23, there are new formatters for std pair, std tuple. Std range, of course, has the range formatter. That's a big feature. I've secretly used that somewhere. It's just, well, printing ranges. Thread ID and stack trace as well. Great. Even more powerful. Regular formattable Constexpr value type, and we hardly wrote any code. Now, the last and one of the, I think, main features in C++23. How do we access values in our data types? So far, I've just defined some simple members, right? Typically, that's not what you do. You don't have public members unless you have very simple value types. Very often you want to hide the actual member and you want to write some accessor. Maybe you also want to assert something, or etc. So in the past, this is probably what I would have written in 99% of the cases, right? It would be a const function that returns a const reference to my member, and that would be all. And that always had the problem, that's not a new feature, that it was very easy, well, it wasn't very convenient to use. So let's say you have a function make contact that returns a temporary object. And now there were two things you could do. Well, there's only one thing you can do. If you wrote order const vac equals this, then this would return a const ref, and you would make a copy of the result. And if you thought in generic programming contexts that you could write this because there's this thing called temporary lifetime extension, then you would produce dangling references because this doesn't work. It compiles, of course, but it doesn't work. So this would work. It would keep the contact temporary alive, but now we're returning a temporary and getting a member of the temporary, and this thing will be constructed, and we are holding a dangling reference. And unfortunately, this was, especially in generic code, when you didn't want the copy, relatively easy to write. So, and the reason, of course, is that the rules of R-valueness didn't work that well for functions. So for members, everything is good. So if you have a member and you access the data member of a type, then the R-valueness gets propagated. So if I have a mutable L-value reference to a contact and I get the emails, then that will be a mutable reference. If I have a temporary, then my emails will be an R-value reference. This is what you want, of course. This is just correct. And now for the simple member function that we wrote, that's all wrong. It always returns the same. We have just one member function, right? No matter what our contact is, it's temporary or not, we always get a const reference. That's bad. Now we introduce ref qualifiers. Ref qualifiers, I still see people ask me about them in interviews when they see our code. So instead of declaring this function const, we can say, yeah, this function should work for const references of a contact. But as always in C++, anything can be a const reference. And const reference binds to anything. So we still have the same problem. I can call this function on a temporary contact. It will compile, and it will do the wrong thing, and it will always lie to me and always tell me, yeah, I'm giving you a const reference to an object that will go out of scope pretty soon. But I can't tell you. But what ref qualifiers were good for, and that's why they were the first part of the solution, is that we could overload on them. And of course, we had to overload on all of them to get this correct. So instead of writing a simple accessor, you had to write all of them. And then you would get the correct behavior again. Yay, we could say, yeah, if I'm calling get on a temporary contact, then this would match, and then I would get an R-value reference to the vector, and I could know I can move out of that vector. I should move out of this vector. So this was somewhat annoying. We did this. I think we wrote a macro to do that for accessors, to generate all of them. But this was not so pretty, and now C++23 gives us explicit object arguments, or short, deducing this. So it looks like a templated function. It looks like a templated function that takes an argument self, and this self is a forwarding reference. But now we have this magic keyword this that tells us, yeah, this argument will bind to, well, the this pointer. So it's the first, usually hidden first argument to any function, the this pointer. And according to the perfect forwarding rules, the perfect forwarding reference will just resolve to, well, a const ref or a temporary or a mutable reference, depending on how we call this. And we'll get the correct behavior again, but we only had to implement one function, which has, well, has a special syntax. But it's not too bad, I think. Yeah, judging by C++ standards, this is a good solution. It's even a good keyword. This is a good keyword. It's what this means. It's not pretty to write, but it's correct. And now we can do this, and we get a move, and that's good, right? We don't do the unnecessary. Well, we don't have to do a copy. We get a move. This, of course, still compiles. It's still wrong. I can't do anything about that. But what we would want here would be, yeah, here, repeat that, right? This is doing lifetime extension, and this, of course, is not. What we would want here is a type that would be magically able to look at the right-hand side and say, yeah, if the right-hand side is an L value, then I'll be a reference. I don't have to copy that thing. But if the right-hand side is giving me an R value, then I need to copy that. Otherwise, this will go out of scope. And so this would be nice to have to get always the most efficient solution. And we built this in our own library as a little macro that you could copy out and use. So this is auto cref is what we call it. And this is just what this does. So this is doing type deduction on the right-hand side. And here we would get an R value. So this would do a move. And if this would correctly return an L value reference, then we would just keep the L value reference and do the efficient thing. And well, the only other thing that you can do if you can't use all these fancy new features and you still want to have programs that are hopefully relatively bug-free is you can, of course, always resort to that, right? You can always say, hey, I don't know what I have to do for R values. I'll just delete those two overloads. And then you at least have the guarantee that you do get correct constref. Okay, so this is my talk. This was the summary. So we follow simplest lifecycle best practices for our types, right? We make value types regular, resource wrappers move only. We make everything Constexpr or at least constinit. Then we can specialize std formatter, and we write accessors using deducing this. Thank you very much. Oh, and I think I mentioned contracts in the abstract, but Timur is here himself to talk about contracts on Saturday, so you can hear it from him himself. So do you have any more questions? We have plenty of time for questions. Did I get anything wrong? I was in a bit of a rush when I wrote this talk.
When we are deducing the TIS.
Sorry? Now the micro's on. Can you repeat that?
Yeah. When we are deducing TIS, can we also not use the template but use like TIS auto instead?
I guess so. Yeah.
Just to make it like
this auto. Yeah. True. Good point. This auto ref. Yeah. Sure.
Is there any benefit in just using structs? Because in that example right now, you could also use a class, right?
Yeah, we consistently use struct. True, in this example here, it doesn't make any difference. No.
I would have, is that on?
I think so, if you speak a bit louder, yeah.
Okay. For the R value getter, would it be an option to just return a value instead of an R value reference?
Sure.
Because then you would also handle the lifetime issue, right?
Yeah.
I mean, you can allow to move away the emails from the R value object out.
Yeah.
Or?
Sure. It's certainly an option. I think here in this case, I try to find something that then works for all cases, and then that returns the R value reference. But if you overload it by hand, of course, you can return the value.
That would solve the lifetime issue, right?
That would also solve the lifetime issue, yeah.
And one additional question to the forward self with the R value. I think the R values are wrong, right? You have standard forward of self, or?
Maybe. Although, I did compile
Well,
this.
I don't know, but normally you would skip the
True,
R
could be.
value stuff
Could be.
over the forward.
Could
so
be.
Yeah.
I think it's just a no-op, right? It's just a no-op because it does the same thing again that I already did. Yeah, it applies to right and loser again. So that's the way it worked, but you are right. I could have left that out. True. Should have, probably. Anything else? Disagreements. Violent disagreements.
Yeah, hi, thank you for the talk. One question, well, maybe one opinion I ask for you is regarding explicit and implicity in class expressiveness. So, for example, in the very early slides, I think on slide. No, I have not noted it. But where you have made this trick with the defaulted move constructors to prohibit the copy constructors.
Yeah.
I think it will result in a different error message when you access or when you try to copy the type.
That is true, of course, but so why I'm a fan of this non-movable, non-copyable thing is that if you Google for how to do that, the first answer is a Stack Overflow question that doesn't get it wrong. So I think it is sure you can do this in every class that you want to make non-copyable, but then inevitably you will forget the assignment at some point or whatever. So I have a typo, it should be non-copyable, but so I like the declarative style, and then if you try to copy file, you will of course get an error message that says file is not copyable because the copy constructor has been deleted because non-copyable doesn't have a copy constructor. So it's clear enough. There's one more step.
Okay, I thought it is maybe more that it tells it's just not available, and I think it's more expressive when it's clearly or stated that it is deleted, since then the compiler will tell the constructor is deleted, so you see it's intended to not copy it. And with this not available, it just tells there is no such constructors there, and so if you do not look it up, you're maybe not sure, is it now intended or on purpose, or is it just missing the constructor?
What happens if you delete? If you delete the copy constructor, you don't get a defaulted move. Isn't that true? If I look at how it is in this table. Yeah. So if you have a default move and you don't have to do anything for the move, you just want to declare the type non-copyable, then suddenly you have to do more work.
Yeah, that's true. Yeah, but it's more expressive. It's the implicit versus explicit.
Yeah, but then you have to, get 4 things correct.
But you get a more expressive error message, I think.
Maybe.
Yeah.
Did you default or delete all of them? Always. Yeah.
Thank you.
It's rather a question of opinion. Like, is the regular, is the simple types are promoted and, well, that's good stuff. But what I experienced that the regular most of the time clashes with invariants of classes. Like, if an invariant of a structure class is not default constructible, then it's not possible to make it still regular. Yeah. So do you have any opinion on this tension?
I wanted to, that's where I thought I would fit contracts into this talk to talk about another type where you have classes with more state and then more invariants, and now you could use contracts to insert those invariants because hopefully you do, and that didn't make it because I thought it was getting long enough. I think. Well, if that's the semantics you need, then that's the semantics you need, right? I mean, you don't force the world into the concepts. If you have a type that is not regular and you can't make it usefully regular, then you can't. I mean, I just mentioned myself the case where comparison is non-canonical maybe and hard. And then, well, don't implement comparison if you don't need it, right? There's no point then. And yeah, that would mean that this type is more complex to use for some templates, but you probably don't want to do that anyway, right? If you have a, like, it's hard to imagine a type that has a lot of invariance and then you're just putting it into a vector and then just do remove if on them. That typically types with more invariance are state machines, are like your web server and stuff, and it doesn't sound really value typey to me. Like having, you can have a bit of both maybe, but well, I would say if it's not regular, it's not regular. I think there is the point, there's also a paper by Bjarne Strostrup about how to write good concepts, and he says, well, the first recommendation when people write generic algorithms is that you should use concepts to express the requirements of your algorithm. And then typically that leads us to require, to write down the minimal requirements we have on the input. And he says, well, that's not such a good idea because then you end up with maybe a lot of slightly different ad hoc concepts. Here I require these 3 operations and here I require those 4 operations. And there he says it's better to come up with like consistent and reusable concepts that have better semantics. For example, regular type. So that's one of them. But A, you can come up with your own ones if they make sense in your application. And B, that's only a strong recommendation. So there must be types that are not regular. Right? Okay, then thank you very much for your attention. Also, I'm here a bit more today. And, well, enjoy the conference. And remember my thing about the bar. That's my quote for the bar. Oh, and have some... Thank you. And take some socks. We have our famous Think Cell socks. Yeah, they're in hot demand. But if we